Hello, I would like to talk about mathematics because I proved a thing and I really like the proof. I think the proof is very pretty. It is because the proof tells a story. It's a rather long proof, but I think it really tells a story and you can draw along. It's purely geometrical and I think the pictures look very nice and the pictures build over time and you can see so much, and I'm quite excited about that proof. And why did I even prove this thing? And why did I think about all that? It's because at the moment I'm working on a project together with Hendrik Van Maldeghem, and it turned out it could be useful and cool and interesting for us to prove certain things. And then this was one of the things that I looked at. And Hendrik helped me, of course, a lot because he answered a lot of questions that I had about parapolar spaces and about Lie incidence geometries of type E6. So this is part of our joint work on a project, and if the article comes out, maybe I can link it somewhere, but it's not done yet. But I wanted to talk about this proof in particular because I find it so pretty. So what are we going to prove today? Today we're going to prove that in a Lie incidence geometry of type E6, which is a parapolar space, if it is a case that every line has exactly s+1 points, then given s+1 lines, L0, L1, ... ls, we can always find a fourth space opposite to all of these s+1 lines, except if these lines form a planar line pencil. This is what we want to prove. And of course, even though I made it into a PhD program, and even though Hendrik already read through my proof, and I read through the proof, it can still be that maybe there are mistakes, maybe I misspeak sometimes. I will put some text on the screen sometimes, and the text should be okay. But it can always be that I misspeak, can also always be that there are some typos, or that there are some real mistakes. I hope not, though, should not be the case, but it can always be. So always think for yourself, question everything, don't believe me, but also don't hate me if I make a mistake. Another thing, this video might not be understandable for everyone. So I'm talking about mathematics that I'm doing for my PhD. That means it might be difficult to understand for people who are not mathematicians at all. It might be difficult to understand for bachelor students. It might be difficult to understand for mathematicians who haven't done anything with incidence geometry in their life so far. I will try to give you all the basic information. I will try to explain well and give you references, but since the math that I've been doing is quite niche and I'm using many different things in the proof, it might still just be difficult. It might be difficult to understand. So this video might just be a video for me and my future self, but I just really wanted to talk about this proof. One more thing that I would like to mention before we start is that maybe you haven't heard of Lie incidence geometries before, but maybe you've heard of buildings before, because buildings appear in different contexts, and I have the feeling that a lot of mathematicians have stumbled across the word building before. Turns out there's a very close connection between buildings and Lie incidence geometries. So I myself am mostly interested in spherical buildings. And I will give you the list of spherical buildings I'm interested in. These are the buildings of type AN, BN, CN, DN, E6, E7, E8, F4. And then there are some others, but they have not been such a huge part of my life yet. So, I will give you a little fun fact. Buildings of type AN correspond to projective spaces. Buildings of type BN and CN correspond to polar spaces. Buildings of type DN correspond to thin polar spaces. And then for the other types that I listed before, we get parapolar spaces. Today we will focus on E6, so buildings of type E6 are parapolar spaces or Lie incidence geometries of type E6. And so, you know, there's some correspondence, and we are interested in the Lie incidence geometries of type E6 in part because they correspond to buildings. In this video I will assume that everyone knows what a point line geometry is, what a projective space is, and what a polar space is. And we can view a polar space as a space that consists of glued together projective spaces. And now, roughly speaking, a parapolar space, you can visualize it as you glue together projective spaces and polar spaces. And what we need for defining a parapolar space is the notion of a point graph or a collinearity graph. So suppose we have a point line geometry, a set of points, a set of lines. Then you can define the point graph or collinearity graph by saying that you draw a vertex for every point, and vertices are adjacent if they are collinear in the geometry. Now let C be a subset of a point line geometry. Then we say C is convex if all vertices of any shortest path in the collinearity graph between any two elements of C are contained in C. And we say that 2 points in C have a certain distance if that is their distance as graph distance in the collinearity graph. So for example, if 2 vertices in the collinearity graph are connected by an edge, then that's distance 1. If they are not connected by an edge, but there is one point, one vertex, such that this point is connected by an edge to that vertex and the other point is also connected by an edge to that vertex, then it would be distance 2, and so on. And now a parapolar space is a point line geometry with 3 axioms. The first one is that the collinearity graph of the geometry is connected. That means points have finite distance. For the second axiom, I will remind you that by the perp of x, we mean the set of all points collinear to x. And now the second axiom is, if we have 2 points x and y that are not collinear, then one of the following 3 things can happen. Either the intersection of the perp of x with the perp of y is empty, or exactly 1 point, or x and y are contained in a convex subspace isomorphic to a polar space. These convex subspaces that are isomorphic to point line geometries of polar spaces are also called symplecta, or short simps. The third axiom is that every line lies in at least one symplectron. And we call a parapolar space proper if it is not a polar space. That means that it has at least 2 symplecta. If we are in a certain geometry, we can construct a new geometry if we pick out one point and then we define the residue of that point as a new geometry. So suppose you have some geometry and you pick out one point, P. Then the residue of P, you do the following. In the original geometry, the point is on some lines. For these lines, so all the lines that contain that point, you draw a point in the new geometry, the residue. Then, if the lines are contained in a plane, then in the new geometry you connect the corresponding points. Then, if the planes are inside a 3 space, then here you put the lines in a plane, and so on. And that is what I mean when I say, or when I speak of the point residue. For us in this video, it's basically only important to get to know a few properties of parapolar spaces of type E6. And I will give you some fun facts very soon. But first let's look at an E6 diagram. So the vertices of the diagram correspond to types. So for example to vertices, lines, planes, sims, 5 spaces. And if we want to know about point residues, we can look at the diagram, look at the vertex that correspond to points, and then see what is left of the diagram if we disregard the vertex that correspond to points. And then we can see what is left is a D5 diagram. And that will also be relevant. So the fact that is important here is that point residues in an E6 geometry are point line geometries isomorphic to geometries of type D55. Geometries of type D55 are also parapolar spaces, and I will tell you some properties. But the most important thing is that D55 is dual to D51, and D51 are polar spaces, so thin polar spaces. But it's usually easier to do something in polar spaces than in parapolar spaces. So if we look at point residues in our E6 geometry, then these are D55, but we might translate them into D51. Look what we can see there, then translate it back into D55, and then again look in our E6 geometry what we can see then. Speaking of diagrams, I already said that the vertices of the diagram correspond to the types. And now if we want to find out which kind of object is opposite to which kind of object, we can also look at the diagram. So in the diagram we can label all the vertices, and these correspond to types, and then we can look at an opposition map and see which vertex maps to which vertex. And when we do that, this is how we find out that in E6 lines are opposite force spaces. And what does that mean? It means that if we have a line and a force space, then they are opposite if no point of that force space is collinear to any point of that line, and no point of that line is collinear to any point of that force space. If we now look at a D5 diagram, we also have an opposition map, but here we can see that lines are opposite lines. Points are opposite points, planes are opposite planes. The only thing is that with force spaces and sims and for prime spaces, there's some switching going on. There we would have to be careful. And just to have it complete, if we look at an A5 diagram and do the opposition thing, then we see that planes are opposite planes, lines are opposite 3 spaces, and points are opposite 4 spaces. But one has to be a little bit careful. In projective space, so A5 corresponds to projective space, opposition is defined in a different way, because we know that in projective space all points are connected by lines. That means it wouldn't make any sense if we said that some object is opposite another object if no point of this object is collinear to any point of the other object. Then we would never have that objects are opposite. In projective space, it just means that the objects do not intersect, then they are opposite. So one has to be a little bit careful and always have to think about what does opposition actually mean in the given geometry. But for E6, which is most important for us right now, it means that really we have a line and a force space, and no point of the force space is collinear to any point of the line, and no point of the line collinear to any point of the force space. I will now give you a list of properties about parapolar spaces of type E6-1. I will not prove them because the video would get way too long. I will give you a reference, but now, unfortunately, I will just give you a list of properties. So let delta be a parapolar space of type E6-1. First of all, then delta is a strong parapolar space of diameter 2. What does that mean? It means that points can have at most distance 2 from each other, and even if they have distance 2, then they are contained in a common simp. Actually, if they have distance 2, then they span. The convex subset spanned by these 2 points forms a simp. Another property that I already told you is that point residues and delta are isomorphic to point line geometries of type D55. Sims in delta are isomorphic to point line geometries of type D51. The maximal projective subspaces that we can find in delta have dimension 4 and 5. Why 4 and 5? Is 5 not more than 4, you may ask? So the thing is, we call a subspace maximal, or a projective subspace maximal, if it is not contained in a larger projective subspace. And it turns out in E6 there are 2 different things that can happen. Either we can have a force space that is contained in a simp but not contained in a projective 5 space, because the simps are D51. That means that there can't be 5-dimensional projective subspaces in there. That means there are 4 spaces that are contained in sims that are not contained in 5 spaces, and then there are 4 spaces which are contained in 5 spaces. If a 4 space is contained in a sim and not in a 5 space, then this is a maximal projective subspace because it is not contained in a larger projective subspace. So these would be the real maximal 4 spaces. If we have a 4 space that is contained in a 5 space, then this 4 space is not maximal. And we will refer to these non-maximal 4 spaces as 4 prime spaces. And the 5 spaces are obviously not contained in any larger projective subspace. So the maximal projective subspaces that we can find in our delta are of dimension 4 and of dimension 5. And there are non-maximal 4-dimensional projective subspaces that we will refer to as 4 prime spaces. Each projective 3 space is contained in a unique projective 4 space and a unique projective 5 space. That is another property. If we have a point and a sim such that the point is not contained in the sim, then the point could be either collinear to no point of that sim, because in E6 points and sims can be opposite, or if the point is collinear to one point of the sim, then it's already collinear to a 4 prime space of that sim. And why a 4 prime space? Because so we have a 4 prime space in the sim, and then this point which is collinear to every point of this 4 prime space, and then the 4 prime space together with the point forms a 5 space. So the 4 prime space is 4 prime because it is contained in a 5 space. In E6, 2 distinct sims either intersect in a point or in a 4 space. If a 5 space intersects a sim in at least a plane, we already know they intersect in a 4 prime space. There are 5 spaces and sims that intersect in precisely a line, but if a 5 space intersects a given sim we already know it intersects in a plane, then we already know it has to intersect in a 4 prime space. For a point and a 5 space, it can either happen that the point is inside the 5 space, or that the point is collinear to a 3 space of the 5 space, or that the point is collinear to a unique point of the 5 space. These are the 3 options, there are no other options. For 2 given 5 spaces, what kinds of relations can they have? They can either be the same or they can be opposite, which means that each point of the one 5 space is collinear to exactly one unique point of the other 5 space and vice versa. Or they could intersect in a point or in a plane, or there's a last option which is a little bit more complicated. The last option is that the 5 spaces are not opposite, but they also don't intersect. So for opposite, we have that there's always a unique point collinear to a given point of the other 5 space. And now suppose we have the 2 5 spaces, but there's a third 5 space which intersects both of them, each in a plane. Then we have for the points in the plane that because they are in a 5 space with the other plane, they all have to be collinear to every point of that plane of the other 5 space, and then already to a 3 space. So then it is not the case that for every point of the one 5 space there's only a unique point of the other 5 space that it is collinear to, but also the 2 5 spaces don't intersect. Suppose we are in this last scenario. Call one 5 space A, the other 5 space that does not intersect A, B, and then the 5 space intersecting both A and B in planes W. And let's say that W and A intersect in a plane epsilon, and W and B intersect in a plane epsilon prime. So we know that for every point in epsilon, it has to be collinear to a 3 space of B containing the plane epsilon prime. Now if we have a point in A that is not in epsilon, then this point has to be collinear to a 3 space of W, and it is already collinear to every point of the plane epsilon, and then it will be collinear to a unique point of B, and this unique point will be in epsilon prime. and then this point in A, the 3 space that it is collinear to for W, is spanned by the unique point in epsilon prime that it is collinear to, and the plane epsilon. Last property I want to mention about E61. Suppose we have 3 different points, P, x1 and x2, such that x1 and x2 are both not collinear to P. Suppose x1 and x2 are on a line together, and then look at the sim spanned by P and x1 and the sim spanned by P and x2. If these 2 sims intersect in a 4 space, then the intersection of the perp of P with the perp of x1 with the perp of x2 is exactly a 3 space. And now there's only one last thing I would like to mention about polar spaces of type Dn. So D51 would be the important example for us today, and it is that there we also have 2 different kinds of maximal subspaces. And in Dn, how we differentiate between them is that if we have these 2 maximal subspaces, we can look at the intersection, and if the intersection has even codimension, then we say they are of the same type, and if the intersection has odd codimension, then we say they are of different types. And that can be, it actually will be important right now, because right now we will prove our first lemma, and there we will need that. And after that lemma, we will prove the theorem. Let delta be a parapolar space of type E6 such that every line in delta has s+1 points. Let P be a point in delta and be a 3 space in delta such that no point of M is collinear to P. Then the unique 4 space containing M does not contain any point collinear to P. Denote the 4 space containing M by C. And now suppose there exists a point Q in C that is collinear to P. Then we look at a sim containing C, and either the point P is inside that sim, but then P had to be collinear to a 3 space of C, which would necessarily intersect M, and that would be a contradiction, or P is not inside that sim. If P is not inside that sim, P is already collinear to the point Q of that sim, so to a 4' space. But we know, because the sims are D5, we know that there are 2 different kinds of 4-dimensional projective subspaces, 4 space and 4' spaces, and so P is collinear to a 4' space of the sim, and C is a 4 space. So they are 2 different kinds of 4-dimensional subspaces. So they have to intersect in odd codimension, and that can either be a line or a 3 space. And in both cases, these would intersect the 3 space M, and it would again be a contradiction. So now we know if we have a 3 space such that no point of the 3 space is collinear to a certain point P, then it is already also the case for the unique 4 space that the 3 space is contained in, that no point of that 4 space is collinear to that point. And that will be useful. Okay, again, let delta be a parapolar space of type E6 such that every line contains exactly s+1 points. Then, given s+1 lines, L0, L1, ... Ls, we can always find a 4 space opposite to all of these s+1 lines, except if the Li form a planar line pencil. This is the theorem that we want to prove. If the Li form a planar line pencil, then it is clear that we cannot find a 4 space opposite to all of them, but the big claim is if this one scenario, if that is the only scenario where we can't do it, in any other scenario we can find a 4 space that is opposite all of these s+1 lines. There's one thing that I forgot to say. So, at the moment we are looking at a Lie incidence geometry of type E6 where every line has exactly s+1 points, and we are given s+1 lines, and we try to find an object opposite to all of these lines. Hendrik and I not only look at E6, and we not only look at lines. It is the case that, for example, for AN, BN, CN, DN, we already proved that given, so for all of these types, we always assume that every line has exactly s plus 1 points. Given s plus 1 arbitrary objects, if they don't form some pencil in some larger space, then we can always find an object of opposite type that is then opposite to all of the given ones. For this video, what I will use in the proof definitely will be that the 5 spaces are point line geometries of type A5. And because we already have the results for A5, I can use in the proof later that in a 5 space, inside a 5 space, I can always find opposite stuff. Then for D5 I will also use it. So our sims are D5, D5-1, so inside a sim I can always find opposite things. But then also if we look at the point residue, then that's a D5-5, but we can translate it into a D5-1, and then for D5-1 we also already have the results. What I will also use, that Hendrik and I already showed that for E6, given s plus 1 different points, we can always find a sim opposite to all of these points. We also have the other way around, so if we have s plus 1 given sims, we can find a point opposite to all of those. And we also have the result for 5 spaces. So if we have s plus 1 given 5 spaces, then we can find a 5 space opposite to all of those. Always except if they form some pencil in some, or like for the 5 spaces, for example, it would be if not all of these 5 spaces intersect in a common plane. So one has to be a little bit careful, but I will be careful in the proof, but I will use these results. I will use that Hendrik and I already showed that under certain circumstances we can always find something opposite. So the proof will go as follows. I will describe to you several different ways of constructing a 4 space opposite all of the Li, but also where these ways could fail. And then we look at the situation when none of these ways work. So where we are always in the bad case. And then this situation will be so specific that we can so clearly that we then can use all of this information to still find a construction for 4 space. So the proof is like we will go through many cases and then pick out the bad cases in every scenario and then look at the bad case, but then we have so much information, and then with all that information we can still find a construction, and then we have the proof. Okay, the first thing we will do is we will consider sims and see what we can do with sims and where are the limits. So first of all, suppose that all of the Li are in a common sim. Because we already know that given s plus 1 lines in a sim, we can find an opposite line. We know that inside that sim we can find a line M that is opposite all of the Li. But then also in our big space we know that opposite that sim where all of the Li's are in, we can find a point opposite that sim. And then we take the line M that is opposite all of the Li in the sim and the point that is opposite to the sim, and then we look at the intersection of the perps of this line and this point. I will denote that point by B. So the perp of B intersected with the perp of the line M, and this forms a 3 space, and then this 3 space is opposite all of the Li, and because it is contained in a unique 4 space, we know that this 4 space is opposite all of the Li. So this is then a good thing that works. So now what if all the Li are not in a common sim together? Then we can put them in different sims. For L0 we will denote the sim by xi0, for L1, xi1, etc. So we have s plus 1 sims. And then because we already have the result for sims in our big space, we know for these s plus 1 sims we can find a point that is opposite all of them. And then this point I will denote by B. And then we do a similar thing again and we look at the intersection of the perp of the point B and the perp of the lines Li. And then we get 3 spaces again, and these 3 spaces we will denote by Ui. And now suppose that at least 2 of the Ui are the same. And then we look in the residue of B. In the residue of B we can see all the Ui. And if at least two are the same, then we know we can find an opposite to all of them in the residue of B. Okay, now suppose that all of the ui are distinct. Then the situation is a little bit more tricky, but we will still look in the residue of B. So if we are in a geometry of type E6, then a point residue is a D5-5 geometry. So in the residue of B, we can see all of the ui, but then we know that we can translate D5-5 into D5-1. So what do we see then? Then we see the ui as lines. And we can find an opposite to all of these lines in D5-1 unless all of the lines form a planar line pencil. And now suppose first that that is the case. So suppose in the residue of B, viewed as a D5-1, all the ui form a planar line pencil. Then we will translate that back into D5-5. Then we again have for the ui, we see them as three spaces again, and they will intersect in a line and be contained in a common simp. Now, if we translate that back into our original space and like go outside of the point residue, that means that the four spaces BUI all have to intersect in a plane. And this is our first bad scenario that we want to remember. And later, if we look at when everything is bad, this will be a component of our very bad scenario. Suppose that it is not the case that in the residue of B, viewed as a D5-1 geometry, the ui form a planar line pencil. Then again we can find a line opposite to all of them. Then translating back into D5-5, we can see it as three space. Then translating back in our E6 geometry, we can see this denoted by U, and that will be opposite all of the Li. So then it's all fine. So the bad scenario is that all the B ui intersect in a plane in our big geometry. We will remember that. So we have considered sims and saw what we can do with them. And now we will look at five spaces and see what we can do with them. So we have all the Li and we now put them in five spaces and we will denote them by Ai. And we can find these Ai in a way that they do not all intersect in a common plane, because there's enough going on. We can find them like that. Then, because we already have the result for five spaces, we can find a five space B that is opposite all of the Ai. And then if we have opposite five spaces, points of the one five space are collinear to unique points of the other five space. So for every point Lij on Li, we can find exactly one point in B that is collinear to Li, and we will denote it by Lij prime. Now we look at the Lij prime, and for every Li we then get a line Li prime that has all the Lij prime, that is in bijection to Li. So we have the line Li in Ai and the line Li prime in B, and every point on Li is collinear to a unique point on Li prime. There's a bijection between them, and these are then the unique points of B that points of Li are collinear to. So suppose all of the Li prime do not form a planar line pencil, then in the five space B we can find a three space opposite all of these Li prime. Then this three space, no point there is collinear to any point of any Li, so this is already good. And then we know again that the three space is contained in a unique four space, and that unique four space will be opposite all of the Li. So this is the good situation. But now suppose that the Li prime in B form a planar line pencil. That will be our bad situation. So now we want to put the two bad situations together. So first we looked at sims and what we can do with them, and found out we can construct a four space that is opposite all of the Li unless things are kind of bad. Then we looked at five spaces and saw that we can construct a four space opposite all of the Li unless things are also kind of bad. And now what if we are in a space and we try it the one way and fail, try it the other way, also fail. So both things are bad, always. And because also we put the Li in sims arbitrarily. They are in several sims, so it has to be bad for no matter which sims, because otherwise we will always succeed. Same with the 5 spaces. So we know, like now, the situation is always bad. The ways we tried it, no matter how we choose the sims or the 5 spaces, always bad. Okay, let's do that. Then we know, so first we put the Li in sims again, find a point that is opposite all of these sims, call it B again, and then we look at the intersection of the perp of B and the perps of the Li, find the 3 spaces Ui, then all of the Ui should be distinct. Then we look at the BUI, and now that they all intersect in a plane, because we know the situation is bad. If it were like this, we would succeed. So this is the situation now. And now we know that the UI, Li span 5 spaces. And now we are kind of like, could we use these 5 spaces to do something? Be more creative. Because for the AI, we really didn't do anything, right? We just said, put them in like these AI 5 spaces. But what if like this is more specific? So what would happen? And we can consider the situation where we look at all of these 5 spaces, UI, Li, and we could find a 5 space opposite to all of them unless they all intersect in a common plane. So there are 2 cases, and we will consider these 2 cases. So first, suppose they do not all intersect in a common plane. Second, suppose they do. First case first. So suppose all of the 5 spaces Li, Ui do not intersect in a common plane. Then we can find a 5 space opposite all of them. And this 5 space we will denote by B. Then we know, because the situation is very bad, that all the Li prime that are in bijection to the Li form a planar line pencil in B. And this plane we will denote by gamma. Now, it is the case that if you have a 5 space and you consider the set of points such that each point is collinear to a unique point of the other 5 space, then it forms exactly the opposite 5 space. In particular, if we have a 5 space and 4 space, it has to be the case, because 5 spaces and 4 spaces are different things, and 4 spaces are not contained in 5 spaces. So a 5 space and a maximal 4 space. It has to be the case that in this 4 space we can find a point that is collinear to more than a unique point of that 5 space. And because we know about E6 and stuff, we know that it then has to be a 3 space. So given a 5 space and a 4 space, there has to be a point in the 4 space that is collinear to a 3 space of that 5 space. And now all the BUI are 4 spaces. So in this whole situation, we know that in each BUI there has to be a point QI collinear to a 3 space of B. Now QI can't be in UI because UI is in the 5 space opposite to B. So for every point in UI it has to be the case that it's only collinear to a unique point of B. So the QI are somewhere else in the 4 space BUI. And because the QI is collinear to a 3 space of B, it has to intersect the plane gamma somewhere, in some point. And this point we will denote by QI prime. So now we know that we have a QI in BUI collinear to QI prime in B in gamma. Remember when we looked at the residue of B and found out that in the residue the situation is bad if all the UI intersect in a line, and then it followed that the situation is bad if all the BUI intersect in a plane. This plane we will denote by beta. And with all of that we can also see that the UI intersect beta in lines, and we will denote them by Ni. So now we also see that because the Ni are in UI, the 5 spaces ui, li intersect beta in the lines ni. So we have these ni's, and then we know that qi is collinear to qi prime in gamma, and the plane gamma, it was exactly the set of points that are collinear to some unique point on some li. So qi prime is collinear to some point of some li, denoted by ljk. And we know, because we are in E6, which is a strong parapolar space, that points are either collinear or symplectic. Qi and ljk are definitely not collinear, so they have to be symplectic, so they span a simp. And this simp we will denote by xi qi ljk. Now, ljk is collinear to the line nj. nj is contained in beta. qi is collinear to every point of beta, so in particular to the line nj. That means, because simps are convex, the line nj is contained in the simp. But also the point qi prime is contained in the simp. And because simps are polar spaces, we know that if we have a line and a point, then this point is either collinear to exactly one point of that line or all points of that line. That means qi prime is collinear to a point, has to be like at least a point, on the line nj. So now the situation is that qi prime is collinear to ljk and to a point on the line nj. But qi prime is in B, which is opposite all of the ui, li. So qi prime is only collinear to a unique point of that space, lj, uj. So then it would have to be the case that ljk is on nj. But that, no, because the point B is collinear to every point on the line nj, but definitely not collinear to ljk, because it's a point opposite to a simp containing ljk. So that is a contradiction. So this can't happen. So that was our case 1. Now we will look at case 2. So now suppose all of the ui, li intersect in a common plane. And this plane we will denote by alpha. We will first do some preliminary observations. First of all, none of the li can be contained in alpha. For that we will just look at L0. Suppose L0 were contained in alpha. Alpha is in the intersection of all ui, li. If L0 is in there, then it is contained in all spaces ui, li. In particular, L0 would be collinear to every point of any other ui that is not u0. But since the perp of some li intersected with the perp of b has to be a 3 space, it would follow that u0 is already the same as other ui. But we assume that all of the ui are distinct because we are in a bad case. So this can't happen. So none of the li is contained in alpha. That is the first observation. Second observation, we have our plane beta and we have these lines ni, which are the intersections of the ui and beta. The ni cannot form a line pencil in beta, because if they did, then one of the ni would have to contain b, and that makes no sense. So we know the ni do not form a planar line pencil. So suppose ui and uj only intersected in a point. Then that point would already have to be the intersection point of ni and nj, because ni and nj are contained in ui and uj, and they are lines in the projective plane, so they have to intersect. So all of the ni have to intersect, and if ui and uj only intersect in a point, it has to be the intersection point of ni and nj. Also, because all of the ui, li intersect in a plane, and not in more, because otherwise some of them would already have to be the same, and that is not the case. So they exactly intersect all in one common plane. then this intersection point of Ni and Nj already has to be contained in the plane alpha. So let's make it a little bit more, I don't know what. Denote the intersection point of Ni and Nj by Zij. Then we have all these Zij in our plane beta. If all the Zij were not on a line together, then they would already span a plane. And they would all have to be contained in alpha. But they would also span the plane beta. So then beta and alpha would have to be the same. And that made no sense at all. So then it has to be the case that all of the Zij have to be on a line together. And we will denote that line by L. But now we found out that all of the Ui have to intersect in a common line. None of them only intersect in a point. They all intersect in a common line. And that line is L. So that is our second observation. So we haven't come the construction of an opposite force space closer, but we know a little bit more about what our bad situation looks like. Now, what do we actually do now? What are our next steps to maybe come closer to constructing an opposite force space? So we have all the Ui, Li that intersect in the planes, so we can't find a phi space opposite to all of them. But okay, let's take L0 and put L0 in some other phi space that does not contain the plane alpha. And this phi space we will denote by A0. And then we can, because then A0 does not intersect with the others in the plane, we have now S+1 different phi spaces that do not all intersect in a plane. That means we can find a phi space opposite to all of them. And again we will denote it by B. So now B is opposite A0, and then all the Ui, Li for I is now in 1 ... S. It is again the case that for the force spaces BUI, there has to be a point in their QI collinear to a 3 space of B. And this will again intersect gamma in a point QI prime. Now for let J be in 1 ... S, then QJ can't be in UJ, because again UJ is in a space that is opposite to B. Now QJ is collinear to QJ prime, and that is collinear to a point, how would I call it, KMN on some Li. And now if LMN were on any of the L1 ... LS, we would get a contradiction as before. Then we would again look at the simp QJ LMN, which would contain the line L and the point QJ prime, and then QJ prime had to be collinear to a point of L, and then it has to be collinear to a unique point, so then the point LMN would have to be on L, and that can't happen because B is collinear to every point on L but not to LMN. So that would be a contradiction. That means the case we now have to consider is if we take a QJ in a BUJ, which is collinear to QJ prime, and then what if QJ prime is collinear to a point on L0? And without loss of generality, this point we will denote by L0. Without loss of generality, we will now only look at Q1 and Q1 prime. We will denote Q1 also just by Q to make it a little bit nicer, and Q1 prime will just be referred to as Q prime. And the point on L that Q prime is collinear to, we will denote it by L, so little l on L. And then, yeah, I already said the point on L0 that it is collinear to is L0. So now we have Q is collinear to Q prime is collinear to this line L, L naught naught. Now we will make another little observation. So the U naught L naught is not opposite B, but U naught L naught still contains the plane alpha, and for alpha it is the case that every point of alpha is only collinear to a unique point of B. And also, since U naught L naught contains L naught and A naught contains L naught, the two 5 spaces have to intersect in a plane. That means the space U naught L naught also has a plane containing L naught, and we will denote it by delta, that is also contained in A naught. And since A naught is opposite B, also for the plane delta it is the case that every point in delta is only collinear to a unique point of B. So even though our 5 space U naught L naught is not opposite B, it contains planes alpha and delta for which it is the case that every point is only collinear to a unique point of B. But also U naught L naught really can't be opposite B, because that is our bad situation, right? It can't be, because of B is already opposite to all of the other UI Li. So at least it has to be the case that there exists a 5 space W which intersects B in a plane and U naught L naught in a plane. And the plane that is the intersection of W and U naught L naught we will denote by epsilon, and the plane upstairs that is the intersection of W and B we will denote it by epsilon prime. Now every point in epsilon is collinear to a 3 space of B. Every point in epsilon prime is collinear to a 3 space of U naught L naught. Also, every point in U naught L naught that is not in epsilon has to be collinear to a point of epsilon prime, a unique point of epsilon prime, because these are just properties of 5 spaces and inside an E6 geometry. So remember our nice little point Q prime in B. Q prime is collinear to the line L, L naught naught in U naught L naught. So it already has to be collinear to a 3 space of U naught L naught. That means Q prime has to be inside epsilon prime. And now think about downstairs, think about the planes alpha, delta and epsilon. For alpha it is the case that all points are only collinear to unique points of B, for delta also, but then for the points that are in epsilon it is very different, because they are all collinear to 3 spaces of B. So the planes alpha, delta and epsilon, like alpha and delta could intersect, but epsilon can't intersect alpha and epsilon can't intersect delta. So our little point Q prime is collinear to every point of epsilon, since the plane and the point are contained in this 5 space W. But Q prime is also collinear to this line L, L naught naught. And since L is in alpha and L naught naught is in delta, these points can't be in epsilon. So Q prime is collinear to a 3 space. That already means that the spaces spanned by epsilon and L and L naught naught have to be the same. And that means that the plane epsilon has to intersect the line L, L naught naught in a point. And this point we will denote by x. And obviously x is a point that is not in alpha and not in delta. I already said that with the properties of 5 spaces in E6, we know that every point in U naught L naught that is not in epsilon has to be collinear to a unique point of epsilon prime. In particular, for every point on the line L0, it has to be collinear to a unique point of epsilon prime. But these points are already the unique points in B that points of L0 are collinear to are on this line L0 prime and gamma. That means it has to be the case that epsilon prime and gamma intersect in this line L0 prime. Now let's look again at the plane alpha. Every point of alpha is collinear to a unique point of B. These unique points in B form a plane again. So there's a plane in B that is in bijection to the plane alpha, and this plane upstairs we will denote by alpha prime. Suppose that the intersection of alpha prime and gamma were empty. So we know that L0 prime is in the intersection of epsilon prime and gamma. On the line L0 prime, there are all the points L0 I prime, which are collinear to a unique point on L0. Since they are all in epsilon prime, they are collinear to 3 spaces of U0 L0. And 3 spaces and planes in a 5 space intersect. So these 3 spaces intersect alpha. And now things are a bit contradictory, right? Because if we have a point in alpha that is collinear to a point L0 I prime and to a point in alpha prime, then these are already 2 points, but they are supposed to be collinear to a unique point. So that means alpha prime and gamma need to intersect, and they need to intersect in exactly L0 prime. So all of the planes upstairs, gamma, epsilon prime and alpha prime, have to intersect in the line L0 prime. Now we will take a closer look at the plane gamma. So gamma is just the plane containing this planar line pencil with all the Li prime. That means, because it's a line pencil, there has to be a point in the intersection of all of the Li prime. We denote that point by D. So since D is in the intersection of all Li prime, it is in particular contained in L0 prime. That means it is contained in alpha prime. That means it has to be collinear to a unique point, D alpha in alpha. But since D is on every Li prime, it also has to be collinear for every I to a unique point Di on Li. So all of the Ui, Li, U2, L2 dot dot dot, US, LS are opposite B. That means in all of these cases the points D alpha and Di have to be the same, because then D can only be collinear to a unique point. But if D alpha is the same as D1, D2 dot 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 ds, then it already means that all of the Li dot 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 ls have to intersect in a point. So now we already found out so much, like we have so much information about how things look in this scenario. And now we can basically start again and get an even clearer look. So what we did is we couldn't find a 5 space opposite all of the Ui, Li. So we put L0 in a different 5 space A0, not containing alpha. And then we found a 5 space opposite to A0 and then all of the Ui, Li for I in the set 1 dot 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 s. And then we found out that with that it already follows that all of the L1 dot 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 ls have to intersect in a point. Now let's put L1 in another 5 space A1 that does not contain alpha. Then we can find a 5 space opposite to U0 L0, A1, U2 L2 dot dot dot, U as LS. And if we do all the same steps again, we find out that all of the L0, L2, L3, ... LS also have to intersect in a point. So what can happen now? Either all of the Li intersect in the same point, or there are two different points. One point in which L0, L2, ... LS intersect, and one point in which L1, ... LS intersect. But this can only happen if S is equal to 2. So either S is equal to 2, and then it could happen that we have three lines L0, L1, L2 that form a triangle, or S could be greater than 2, but then all the Li have to intersect in the same point. Let's first look at the triangle case. So assume S is equal to 2. So suppose all the Li form a triangle. Then they form a plane. Then they are all contained in a common 5 space. Then to that 5 space we can find an opposite 5 space. Then in the opposite 5 space we again get a plane that is in bijection to the plane formed by the Li. So in the opposite 5 space we have this one plane where points are collinear to points on Li, and all the other points in the 5 space not collinear to any point on any Li. In a 5 space opposite the plane we can find a 3 space. So in the opposite 5 space we find a 3 space where no point is collinear to any point on any Li. This 3 space is contained in a unique 4 space, and that 4 space is opposite to all of the Li. So then we again have an opposite 4 space. Now suppose all the Li intersect in the same point, d alpha. It was our assumption from the beginning that the Li do not form a planar line pencil. That means the Li are not in a common plane together now. That means we can find a 5 space C that is locally opposite in the residue of d alpha. Now, this 5 space, there are many sims that intersect that 5 space in 4 prime spaces. And we take any sim that intersects this 5 space in a 4 prime space U prime, not containing d alpha, and denote that sim by xi. So in xi we now have this 4 prime space U prime, and now any, because in sims 4 prime spaces are opposite 4 spaces, we can now take a space opposite U prime. That will be a 4 space. You will denote it by U, and then U is a 4 space that is opposite all of the Li. And then again we managed to construct a 4 space that is opposite. And that was all. That was the whole story. We had bad cases, bad cases, bad cases, but in the end we knew so much that still somehow we could figure out how to construct a 4 space opposite all of those given lines. And that was everything. And that is all I wanted to talk about today. Thank you very much for watching, and goodbye.